Hello, everyone. Welcome to my public lecture. Hmm. Right, let me begin with a deceptively simple question. How do we know how many fish are in the ocean? How do we know it? We cannot simply, right, do survey on this. And we cannot count every fish. We cannot see most of the ocean. Fish move across enormous distances. Their populations change with temperature, currents, food availability, predators, pollution, habitat destruction, and perhaps most importantly, fishing pressure. Yet governments must make decisions such as how many fish can we safely catch? Which areas should be protected? When should fishing be restricted? Is a population recovering or collapsing? What will the fish population look like 5 years from now? For centuries, fisheries management has largely depended on biological surveys, catch statistics, mathematical models, and the expertise of fisheries scientists. But we are now entering a different era. AI, artificial intelligence, can allow us to move from sorry, periodically, yeah, periodically measuring the ocean to continuously learning from it. The goal is not simply to make fishing more efficient. The deeper goal is, can we use intelligence to understand an ecosystem well enough to harvest from it without destroying its ability to regenerate? So this is the real scientific challenge. Now, the first part that I want to share with you is, what is a fish stock? First, we need to understand what we are predicting. A fish stock is essentially a population of a particular fish species or biologically meaningful population unit that is managed as a resource. So scientists are interested in several variables. There are five variables. The first one is biomass, how much fish exist. And the second one is recruitment, how many young fish are entering the population. And the third one is fishing mortality, how strongly is fishing removing fish. And the next one is natural mortality. How many fish are dying from predators, disease, age, and environmental causes? And the last one, but not the least, which is spawning stock biomass. How much reproductive biomass remains? So let's look at the simplified population equation, which will look like this. I'm going to share it on the blackboard, not the blackboard, sorry, whiteboard here, the equation of this. Okay, I'm going to put it up here, the equation of it. So this is a simplified population equation that would look like this. So this will be the population equation. So biomass at time, recruitment, growth, catch, natural mortality. So here, when we look at this population equation, traditional stock assessment attempts to estimate these components. The problem is that we do not directly observe most of them. What do we observe is their fragments We catch data, we survey data, we acoustic signals, and we fish sizes and fission effort, environmental conditions, and then we attempt to reconstruct the invisible population. This is where AI becomes extremely intriguing. Now, um, let's move on to the next part, which is the the ocean is becoming a data-rich environment. Um, okay, let me stop sharing the screen. So the modern ocean is generating extraordinary quantities of data. Let's consider the sources. So the first one, satellites. Satellites can observe a lot of varieties of things: sea surface temperature, chlorophyll, ocean color, currents, productivity, habitat conditions. And the second one would be acoustic sensors, right? Acoustic, acoustic, acoustic sensors, not acoustic gitter, okay? So sonar can detect fish schools beneath the surface. So AI can potentially transform acoustic signals into estimates of abundance, species, composition, school structure, and distribution. And the next device will be underwater cameras. Computer vision can identify and count fish automatically. So to give you an example, NOAA Fisheries, right? NOAA, NOAA Fisheries. Mm, okay, let me share it on screen. Let me put it on the whiteboard again. So the company name is NOAA, NOAA Fisheries. Yeah. So NOAA Fisheries, for instance, has developed AI initiatives for automated underwater image analysis to produce species-specific and size structure abundance estimates for stock assessment. So the next one is vessel tracking. AIS and other vessel monitoring technologies provide information about where vessels travel, where they fished, fishing intensity, potential suspicious behavior. And the next one is electronic catch records. Fishing vessels increasingly generate digital records of species, weight, location, time, gear type. And the next one is environmental sensors: temperature, salinity, oxygen, acidity, and other variables can explain why fish populations change. So the result is a new paradigm. So the fishery is no longer represented. Sorry. Oh, what was it? Yeah, the fishery not represented, sorry. Um, the fishery is no longer represented by one data set. So it is represented by a multi-dimensional ecosystem data stream. Now, in a while, we're going to look at the next formula. So now, let's move from statistics to machine learning. So traditional fisheries models are extraordinary variable, yeah, and variable and valuable. So we should not imagine that AI is replacing fisheries science. Rather, the most promising direction is AI plus traditional fisheries science. Yeah. So NOAA, I put it NOAA, NOA, that company just now, describes stock assessment as the scientific process of analyzing the condition of fish stocks and estimating sustainable yield. So different models are selected according to the quantity and quality of available data. Um, okay, let me search here and I'm going to put it here. Um, yeah. So, oh, yeah, where was I? Yeah. So it's about NOAA and OAA. So NOAA, it's the National Oceanic and Atmospheric Administration Home, the organization. You can look it up into do any type of search and you can read more on it if you want. Machine learning acts another capability. So instead of specifying every relationship mathematically, we can allow an algorithm to learn relationships from data. So this is it to give you an example of it. So this will be the formula, right? So function of fish biomass equals function of temperature, chlorophyll, catch, afford, habitat, currents, recruitment, and I dots. So a machine learning model attempts to learn the function. Possible approaches include random forest, gradient boosting, support vector machines, artificial neural networks, recurrent neural networks, transformers, Bayesian models, reinforcement learning. But there is a critical distinction. Yeah, there is appearance significant thing. Prediction is not the same as understanding. An AI system may accurately predict that biomass will decline without understanding the ecological mechanism causing the decline. That distinction becomes extremely crucial when management decisions affect people's livelihoods. So now in this part, I want to talk about the hybrid future, biology plus AI. One of the most promising approaches is the hybrid model. So instead of asking, should we use traditional fisheries models or AI, we ask, how can AI augment scientific models? So research on machine learning-based stock assessment has explored hybrid approaches in which conventional stock assessment estimates are combined with machine learning to improve predictions of variables such as recruitment and spawning biomass. So this is scientifically powerful since traditional models contains domain knowledge. Well, AI contributes non-linear pattern recognition, high-dimensional data integration, predictive flexibility, automated feature discovery, and traditional models would contribute biological constraints, interpretable parameters, establish ecological relationships, scientific theory. So the future may be neither purely mechanistic nor purely data-driven. So it may be mechanistic plus statistical plus machine learning. Now, how about we go to the future now? And we're going to imagine something. Okay, before that, let me take a sip of water. Okay, so imagine, yeah, now imagine that we want to predict the biomass of tuna the tuna fish 6 months from now. Well, a traditional system might analyze historical catch and survey information. But what AI would do, an AI enhanced system could simultaneously consider historical biomass, fishing effort, sea surface temperature, chlorophyll, ocean currents, prey availability, spawning locations, vessel activity, climate oscillations, satellite observations, acoustic surveys. So the model produces, right, something more sophisticated than, well, the stock is 500,000 tons. Instead, it could produce like this. I'm gonna share it here. It could produce like this. So instead of just giving an overall estimation of 500,000 tons, it would give like this. So expected biomass, 480,000 tons, 90% prediction interval, which was between these two figures, right? 390,000 and 590,000 tons. And probability of falling below the management threshold is 27%. So this is a profound change. We are moving from a single estimate toward probabilistic decision making under where? Uncertainty. Right. Um, Now, even the field, right? The field that we are exploring, which becomes even more interesting. Fish do not live as isolated mathematical variables. A tuner does not know that it belongs to a tuner dataset. It lives inside where? An ecosystem. It eats other organisms. It competes with other species. It is effective, yeah, it is affected by temperature. Its prey respond to environmental conditions. Predators respond to its abundance. Fishing affects multiple species simultaneously. Now, in a study, right? A 2026 study introduced mailed, yeah, maelstrom. Well, let me put this word for you here. This one. Maelstrom. Okay, so what is this? It's a neural network. Okay, let me stop sharing for now. It's a neural network-based multi-species stock assessment approach that integrates fishery-dependent and fishery-independent data and forecast abundance under different fishing effort scenarios. The researchers benchmark it against a conventional stock assessment framework. So this represents an important conceptual transition from predicting individual stocks to modeling interacting ecological systems. So this is much closer to the real ocean. AI can also predict where fish will be. So stock prediction asks how many fish are there? But fisheries management also needs to ask where are they? This creates a second major AI application. Now, I'm going to show you the species distribution modeling. Um, I'm going to share it on the whiteboard here. So this is the special distribution formula. Yes, special distribution formula, which is the AI can combine these things. Species distribution equal function of these things, temperature, oxygen, depth, salinity, food, currents, habitat. This is the same thing, the previous one. So the result can be a dynamic probability map. For instance, where is suitable habitat for a particular species likely to occur tomorrow? This can support sustainable fishing, marine protected areas, bycatch reduction, habitat conservation, search efficiency. AI could therefore potentially help fishermen spend less time searching while reducing unnecessary fuel consumption and ecological impact. Now, we are reaching the important stage now. Prediction alone does not manage a fishery. A manager needs to decide what should we do. For instance, AI predicts, well, there is a 35% probability that biomass will fall below the biological limit. So what should the government do? Reduce catch by 10% or 20% or seal the area or change fishing seasons or change gear or do nothing at all. So this is where decision support systems and increasingly reinforcement learning become relevant. So reinforcement learning can simulate management actions and learn which strategies perform well under different ecological and economic conditions. So now let me give you the sample, another formula of it. So the objective is not simply just like this. Okay. Um, share it here. Not just like this. Objective is not something just like this. Not simply mass fish catch is closer to mass fish than left ecological sustainability plus food security plus economic welfare, right? So which subjects to biological constraints. So this is a much harder optimization problem. All right. So now, who owns the prediction then? Now I want to move from technology to philosophy. Imagine an AI system tells a government, hey, fishing has to be reduced by 40%. A fishing community responds, our families depend on this fishery. So who is correct? AI? Okay, let me stop sharing this. Is it AI or the fishermen or the scientists or the government? But I just want to say that the AI should not be the final authority. An algorithm has no democratic legitimacy. It does not experience poverty, it does not understand cultural traditions, and it does not carry the social consequences of a closed fishing season. So AI should be a decision support system, not a yeah, a decision support system, not a decision sovereign. Yeah. Um, Recent work on digital transformation in fisheries has highlighted concerns about bias, interpretability, and accountability, particularly since small-scale fisheries may be underrepresented in formal data sets. So this is crucial. If the data are biased, the prediction can be biased. If small fishing communities generate less digital data, AI may see them less accurately, and what AI does not see can become politically invisible. So, there is a great danger that accuracy is not enough. Suppose an AI model achieves excellent prediction accuracy on historical data. This does not guarantee it will work when ocean temperatures change, ecosystems shift, fishing behavior changes, a new disease appears, climate regimes change. This is called distribution shift or concept drift. Um, so Fisheries AI must be continuously evaluated. We need out-of-sample testing, uncertainty quantification, model ensembles, sensitivity analysis, causal reasoning, ecological constraints, human expert review. So the question should never be how accurate is the AI? It should be how reliable is the AI when the world changes? Now, there's also another powerful application that I want to share, which is IUU fishing, right? IUU fishing, which is illegal, unreported, and unregulated fishing, which can not determine, sorry, which can undermine sustainable fisheries. AI can analyze vessel trajectories and identify suspicious patterns. Um, for instance, unusual rendezvous unexpected movement patterns, fishing in restricted areas, prolonged activity in unlikely locations. The algorithm does not necessarily prove illegal activity, instead, it creates a risk score. So, authority can then focus limited enforcement resources on high risk cases. AI does not replace enforcement, it makes enforcement more intelligent. Now, let us now imagine one more time for the future. Suppose we create a digital twin of a marine ecosystem. Yeah, a digital twin of a marine ecosystem. A digital twin is a computational representation of a real system that is continuously updated with observation. So let me rephrase this definition. Um, let me repeat this definition. So for who do not know what is digital twin, a digital twin is a computational representation. Yeah, a computational representation of a real system that is continuously updated with observations. So our virtual ocean receives a lot of things like satellite data, vessel data, acoustic data, environmental measurements, biological surveys, catch data, and we could throw these questions. What happens if fishing effort increases 10%? What happens if ocean temperatures rises 2 degrees Celsius? What happens if a spawning area becomes protected? Or what happens if we um, reduce um, juvenile catch? What happens if two species decline simultaneously? So the computer simulates possible futures. The manager does not ask what will definitely happen. Instead, which management strategy remains safest across many plausible futures? So this is a much more sophisticated definition of sustainability. So I want to describe the emergent AI fishery system as 5 layers. Yeah. So layer one as an observation, there includes satellites, cameras, sonar, sensors, vessels, and surveys. And layer two is data integration. AI brings heterogeneous data sets together. And layer three is machine learning estimates biomass, recruitment, distribution, mortality, habitat suitability. And layer four would be simulation. Digital models explore alternative futures. And layer five would be scientists, managers, and communities evaluate possible interventions. So the ultimate system could become like this. Okay, I will shut it on the whiteboard again. So here, so this is the closed loop adaptive management system. Observe, learn, predict, simulate, decide, observe again. So this is a cycle. Yeah, all right. So, okay, now we're talking so much about events, fisheries. So, what could this mean for developing countries? This is especially crucial for countries whose fisheries are central to food security and livelihoods. AI does not necessarily require enormous fleets of research vessels. A combination of smartphones, low-cost sensors, satellite data, cloud computing, open source AI, local ecological knowledge could potentially create useful monitoring systems even where traditional scientific infrastructure is limited. But technology transfer alone is rather insufficient. A sustainable AI fisheries program requires, well, trained scientists. Mm, it costs money and reliable data governance and local participation, transparent algorithms, institutional capacity, long-term funding, and AI cannot compensate for the complete absence of trustworthy data. So in fact, AI amplifies the quality of the data it receives, including its weaknesses. So what is the hardest problem? It is not building a neural network or it's neither collecting more data nor developing a larger computer. The deepest challenge is how do we build AI systems that remain scientifically trustworthy when the ecosystem itself is changing? So climate change is turning the ocean into a moving target. Fish distributions are shifting, food webs are changing, extreme events are becoming increasingly important. Historical relationships may become unreliable. So the fisheries AI of the future must be adaptive, explainable, and certainly aware and ecologically constrained. And we often spoke about smart fisheries, but I think we should aim for something greater, not simply smart fishing, but intelligent stewardship. Because the objective is not to catch the maximum possible number of fish. The objective is to maintain a system in which fish populations remain healthy, ecosystems remain resilient. Fishermen can make a living, communities have food, future generations inherit productive oceans. So the best AI system is not the one that catches most fish. It is the one that helps humanity understand when enough is enough. Okay, let me stop sharing the screen. So I just want to finish off this lecture with three statements. First, AI will not replace fishery scientists for sure, However, it will give them new instruments for seeing patterns that are impossible to observe manually. And second, AI will not eliminate uncertainty. Uncertainty will be still ongoing as long as the art lives. It will help us quantify, communicate, and manage uncertainty more intelligently. And the third and most importantly, technology cannot create sustainability by itself. Sustainability is ultimately a human decision. We decide what kind of ocean we want. We decide how much we are willing to take. We decide what we will protect. And we decide whether the rights of future generations matter. And the next generations of fishery managements may look like this. A satellite observes the ocean. A sensor listens beneath it. A camera identifies the fish and a machine learning model estimates the population of the fish. A digital twin simulates possible futures. So, and then a human being makes the decision. That final step is so much matters. The reason is the purpose of AI should never be removed should never be to remove human responsibility. It should be to make human responsibility better, yeah, better informed. So the ultimate question of AI-driven fisheries management is not, can artificial intelligence predict fish? The more profound question here is, can human intelligence augmented by artificial intelligence, learn to take from nature without taking away its future. So we got to learn to take, yeah, from nature without taking away its future. So that is the real promise of AI-driven fisheries management, and perhaps that is the real test of intelligence itself. So thank you. If you want to read more, I'm going to share the references for further reading on my lecture. If you want, um, I will put it here on the whiteboard. Okay. But I'm going to clear this off. So this is the references for further reading if you are interested to read more. So I believe that you've learned something out from this lecture, and so you can read more. All right, let me stop share the screen. All right, so I see you in my next interesting lecture. Naming my Naming my public lecture is interesting. I hope it is intriguing so much for you also. So I see you in my next lecture, and until then, God bless you. Take care. And remember, God loves you so much, and have a lovely week ahead for you. Bye.